simply. Meaning that if you have 2 raised to the power minus 3, it means 1 over 2 raised to the power 2. 2 raised to the power 3, I mean. If you have 5 raised to the power minus 1, minus, maybe minus 7. This is equal to 1 over 5 raised to the power 7. So this is 1 over what? 2 raised to the power 3 is what? 8. 5 raised to the power 7 is what? 5 raised to the power 7 is what? 5 times 5 times 5 times 5. 27 times.
7,800, or no, 78125.
7, 8, 1, 2, 5. Good. So this is very, very simple. What about the fractional index law? So, number 6. Fractional index rule. Which says that if you have a power m over n, this is equal to n roots of a power all power n. So the idea is from this, it means that if you have 9 power 3 over 2, so this is equal to the roots of 9 power 2.
Isn't it?
Power 3, I mean. If you have this, a power this, that means the n here, the numerator of the power, will be the roots, nth roots. Ym will be the power of everything. That's what we did here. Right? So this simply means you want to find a number that when it multiplies itself, it will become what we have inside here. And that number is 3. Right? This now is 3. That number is 3. 3 raised to the power 3. This will give you 27. Hope this is clear. You can also see this with an example of 8 power 2 over 3. Oh, sorry, this should be power. 8 power 2 over 3. I want you to apply this. If you apply this here, it means our end is the 3 of 8 all power 2. Let's just keep the power aside first. It means that we want a number that when we multiply it 3 times, it will give you 8. Just like here, we needed a number that when we multiply it 2 times, it will give us 9. It was 3. So that which number can we multiply 3 times to give 8? 2, correct. So here we have everything here now is 2. 2 raised to the power what? 2. This is equal to 4. Is that correct? Just pay very much attention to all this rule. So I'm taking my time to explain this in detail so that by the time we get into applying all this to initial equation, it will be very, very easy for us. Then we go with very high speed. Okay, so the next one is product power rule. We said this earlier, where we said that this is reward. This is 7. So, product power rule or law. It means that if you have A and B, all power m, this is equal to, this will distribute into our two variables, which is A power m and B power m. And also for division, if you have A over B all power m, this is what? A power m over B power m. Is that correct? Good. So maybe the final one says that number 8. I don't know if I should call it equating the power or equation of power. Equate, let's say equating the power. So this simply means if you have an equation where you have two bases that are the same, you just cancel out the bases and equate the power. Look at what I mean. Anyway, after solving, if you have anything like A power m is equal to A power n, you do what? You equate this power, cancel out, and equate the power. This will imply that m is equal to n. Is that clear? Good. So, before we, I think we have to just go straight and look at the rules of indices, the rules of logarithm, because there is a kind of relationship between indices and logarithm. Right? So look. Logarithm. So logarithm is simply a number of a number. Logarithm is the logarithm of a number. Logarithm of a number, let's say A to its base B is equal to maybe n. Means that you want to get the base of this logarithm, which is b power what? Power n. That when you take this to the base of this will be equal to what? A. So this is kind of the relationship between logarithm and indices. Logarithm and indices. So let's look at this. So now if you want to look at the logarithm of log 32 base what? Base 2 is equal to what? So we want to find this number here, the logarithm of 32 base 2, in the sense that if you take the log, if you take these 2, power whatever we have here, let's just name this a variable. Let's use this as a variable. What do we call this? Name any letter.
X.
X. So let's say X. This raised to the power X is equal to 32. Right? So we want to, it's saying that whatever number that we get of this X means that whenever you take the degree of this and multiply it and raise it to the number of times of this X, it will give you 32. All this is clear. So mathematically, here we have 2 raised to the power x. You can simplify this thing further to give 32 is 2 raised to the power 5. 32 is 2 raised to the power 5. 2 raised to the power 5. You can see that from our law of the 8th law of or 8th rule of indices, whenever you have two bases in an equation, you only do what? You have to subtract, you have to cancel out and equate the power. Hence, x is equal to 5. Hence, therefore, log 32 base 2 is equal to x. Good. What about if you have log? What about if you have log 81 base 3? Log 81 base 3 equal to which variable are you using now?
B.
B. So from this now, we want to take 3 raised to the power b is equal to 81. Hence, you have 3 raised to the power b equal to 3 times 3 raised to the power 3 will give you what? 27. 3 raised to the power 4 will give you 84, but check. 3 raised to the power 4 will give you 84. 81, I mean. That means 3 raised to the power 4. I can see that this has the same base. You cancel out. Hence, b is equal to 4. Let's solve maybe one more or two. What about log 27 base 9 equal to which variable are we using now?
C.
Let's use C. We have not used C for a while now. So log 27 base 3 will give you what? Hence, from this, log 81 base 3 is equal to 4. Good. What about this? Can we try this out? In 2 minutes. Let's just try this out. You know, mathematics is a kind of, there are so many concepts that it's not really good to teach them differently. Just like when you say simple interest and compound interest. So, even when you teach in simple interest alone, teaching them simultaneously will help the very, very easy comprehension of the both. Simple interest, compound interest, HCF and LCM. That's highest common factor and lowest common multiple. Right? And what are the mathematical expression, mathematical equations? It's more like singular and plural, present tense, past tense. When you teach them this way simultaneously, to help to see the relationship between those concepts. That's like differentiation and integration. Just like what and what again? What and what? Some concept that you have to teach simultaneously too. What and what? So what's our C?
3 over 2.
3 over 2. Who has got 3 over 2? Good. So from this, we say 9 raised to the power C equal to 27. 9 raised to the power C equal to 9 raised to the power 2 will give you 27. Is that clear? That raised to power 2 will give you 27. 27. Wait. No, 9 raised to power 2 will give you 81, not 27.
3 over 2.
Wait. So what do we do?
Take the log of both sides to get C to be the subject.
Okay. Are we taking log? No, we are not taking log of both sides. Okay, this question is correct. So, we have 27 here. 3 raised to power 3 is what?
27.
3 raised to power 3 is 27.
Yeah.
3 raised to power 3 is 27. That means you have 3 raised to power 3 at 27. 3 raised to power 2 is 9. 3 raised to power 2 is 9. From this, you apply this law. Here. Where is it? Yeah, this. You multiply this. M plus times n. Hence, you have 3 power 2c equals 3 power 3. It has the same base. Using the 8th rule. 3 will cancel 3. Hence, you have 2c equals 3. From here, we have 2c equals 3. Divide both sides with coefficient of c. Divide this side with 2. Divide this side with 2. Hence, you have c equals 3 over 2. Let's solve this last one before we go into the rules of indices. Rules of logarithm. So, log 1 over 2 base 2. Log 1 over 2 base 2 is equal to what? Which variable are we using now?
W.
W. So from this, we say 2 raised to the power W equals 1 over 2. So what do we do next? We apply one of these rules here. You can see some of these things that we are applying here is from this. Something index. Negative index rule. Where is it now? Look at it, negative index. So if you have this, and we are taking it back to its original form, this means 2 raised to the power W equals 2 power minus 1. Since they have the same base, hence W is equal to minus 1. Good. So the laws of indices, laws of logarithm, laws or rules of logarithms. The first one is similar to our product multiplication law or rules of indices. Where we have log mn 1 log mn base b is equal log m base b plus log n base b. This simply means if you have example, this simply means if you have something like maybe log 30 base 2, this implies that this is log 6 base 2 plus log 5 base 2. This is very, very similar to this previous law, the law of indices. So if you have log 72 base 2. You have log 72 base 2. So this is empty as 8 times 9. That means log 8 base 2 plus log 9 base 2. Is that clear? So this is very, very similar to our multiplication law. Then for division law of logarithm, say that if you have log, our division law of logarithm says if you have log m over n base b, this is equal to log m to base b minus log n to base b. I see this is very, very similar to this law. Hence, if you have log 100, example, you have log 100 over 3 base 2. This is equal to log 100 base 2 minus log 3 to base 2. As simple as that. Then the next one is, and also you can transfer this back. If you also have maybe log 3 to base 81, maybe log 81 base 3 minus log 9 to base 3. This implies log 81 over over 9, all base 3. Just like we have in our law of indices. So you can transfer this back, change this back. If you have something like this, you can retrace it back, simplify it back to this form. So in the same form, we can do the same thing here in logarithm. Good. So the next one is, just like this one, we already applied this when we were solving some problems from simple interest or compound interest. So if you have log, this one is 3. So if you have log of any number, and raised to the power k, log any number raised to the power k, base b. This implies k log n. Remember when we did like taking of log of both sides in simple interest, right? Or the compound interest, compound interest. So this is what we will apply. Right? So let's see some examples. So if you have log 10 base 100, if you like log 100 base 10, example. If you have log 100 base 10, this is equal to log base 10. 100 is same thing as 10 raised to the power 2. 10 raised to the power 2. Hence, this is equal to 2 can come down, 2 log 10 base 10. Again, there is another case under this. So the case now is, whenever you have a log of any number to its base is 1. So the condition, a sub, you can say this is a special case, or maybe, I don't know what to call it, maybe it shouldn't stand on this code, it's more like a sub from this. So special case. Special case. Log of b to base b is 1. Hence, log of 100, 10 to base 10 from here is 1. Hence, here we have 2 times 1 equal to 2. So, log 1000 to base 1000 will give you 1. log 5,000. Let me think like Andrew. Like 5,000 to base 5,000. We give you 1. Hope this is clear. If you have log 12, log 140 base 144 base 12. This is equal to log 12 raised to the power 2 base 12, which is equals to log 12 base 12. From this special case, you have 2 times, this will be 1, which will give you 2. Likewise, anything, maybe log 49 base 7 equals log 7 raised to the power 2 base 7. Hence, you have 2 times 1. Hence, you have 2. So sometimes it mustn't be this linear, maybe having 2 all the time. You could have a raised to the power 3. Just find a way to simplify. Just make sure you are familiar with all these basic multiplication, even at least all this lowest step. So finally, the log of 1 to any base is 0. The log of 1, so this one should be what? 4. The log of 1 to 0 base so log 1 to any base is 0. Any base is 0. I think we can be able to show this by stating, so from this, just like we stated from that basic law of anything raised to the number power 0 is 0, and we showed how it is true here. I think we can show it here too. If we say the log of b to base 1 is equal to log of so we already satisfied that anything raised to the number, anything raised to power 0 is 1. If we say b raised to power 0, it follows, right? And from this basic law, there is this basic law. From this law, this can come down, the 0 can come down. And if this 0 comes down, we have 0 times log b to base b. You have 0. Is that clear? So now, having gone through all this detailing of how to conceptualize and comprehend these basic rules, laws of indices and log gradient. So we'll now go over to how to apply all this to solve problems of indices, log gradients, initial equations. Is that clear? Okay, so the first problem. So the first problem is Let's evaluate this. Evaluate 5 raised to the power x times 20, 5 raised to the power x minus 1 over 1, 2, 5 x raised to the power 4 x plus 1. Let's simplify this. Solution. So the first thing is from here. You want to simplify some of these big numbers into its lowest term. Like you know that 25 is the same thing as 5 raised to the power 2. Is that correct? Hence you have 5x times 5 raised to the power 2, x minus 1. What about this? 125 is the same thing as 5 raised to the power 3. Is that correct? 5 raised to the power 3. It is equal to 5 raised to the power 3 here. We still have x minus 1 plus 1. From this, from the basic law of indices, remember the multiplication law says if you have two numbers of the same base, multiply each other, you can add the power, right? So that means you don't need to disturb ourselves with splitting this into pieces. So we can just do this. Take one base, 5, you have x plus this what's in here. Alright? Let's open up this. Let's distribute this 2 into this. So we have 2x minus 2 over what? 5 over 3x plus 1. So this is equal to what? Also remember the law of the second law of division that says when you have two bases dividing each other, you bring one base and do what? And subtract the power. You can see it, you can reason it from that angle, and you can also reason it from the angle of the negative index law. That says that if you have a power minus n is equal to 1 over a power n. You can reason it from that angle, and also the angle of division of indices. So applying that knowledge here. So this should be equal to 5 power x plus 2x minus 2. All this minus 3x, no, minus 3 into x plus 1. All we need to do is just simplify what we have in our power. Just like as if we are solving an expression, a mathematical expression. If we do that, we have 5 raised to the power. Here we have x plus 2x minus 2 minus, remember you have to recognize this negative sign here, minus 3x minus 3. So this is equal to x plus 3x will give you what? 3x. So you have 3x here, minus 3x gives you 0. That means we are left with our number, a constant in the power. Which is what? Minus 2 minus 3. Hence you are left with what? 5 minus 5. We want to evaluate and simplify to its lowest form. So from this, using the rule of negative index law, which says that a power minus negative n is equal to 1 over a power n, right? So this is equal to 1 over 5 power 5. If you are following to this point, thumbs up please. You need more clarification at any point. It's very clear, right? Good. What we are doing, we are applying the knowledge of everything we have done. All this through basic operation. So that's why when I was preparing for this topic outline, it took me a lot of time to be able to make sure that everything is sequential. Right? So this is what 1 raised to power 1 over 5 times 5 times 5 times 5 times 5, which is equal to, what do we have? 1 over what?
3,125.
3,125. Correct. So this is the first example. Can someone clean up that last side? So the next one is so I want to simplify so, by me looking at this thing looks scary, right? Looks scary. So, well, all you need to do is just take it one after the other. Alright, so you only need to just apply our basic rule, which is, if you start from this 100, if you start from here, this 100 power r power 8, this is equal to 100 r power 8, and square root means 1 over 2, right? It means 1 over 2, and this is equal to, this 1 over 2 is distributing into everything that we have here from the law of product law, what do you call it, law, product law or rule. Hence we have 100 power 1 over 2 times r power 8 times 1 over 2. Hence, this is equal to, this is the same thing as 10 raised to power 2. 100 is the same thing as 10 raised to power 2 times 1 over 2. R power, hence here you can see that we have 8 times 1 over 2. 2 we cancel 2. Hence you have 10 times r raised to power 4 divided by 2. 4 times 1 will give you 8 times 1 will give you 8. 8 divided by 2 will give you 4. Hence you have 10 r power 4. So we have simplified this. Hence you can have something like this. (160) r squared plus 71 r power 4 plus 10 r power 4. You can see that these are like terms. They have the same variable r and also of the same form, same degree. That means you can do our basic operation, addition and subtraction, which will give you 81. Hence, this is equal to 160 plus 81 r power 4. So it has been reduced to this form. So what do we do next? Let's just pick up this root 81 r power 4 and deal with it and bring it back. So how do we handle it? If you pick up this, we have root 81 r power 4. This is equal to 81 r power 4 power 1 over 2. So if this thing should distribute into all these parentheses, you have 81 power 1 over 2 times r 4 times 1 over 2. But 81 is the same thing as 9 power 2. We have times 1 over 2 times r 4 times 1 over 2. 2 cancel 2. 4 cancel 2 here, we have 2. Hence you have 9 r power 2. It means that everything here is 9r power 2. Hence, you substitute the value of everything here as 9r power 2. Hence, this is equal to 160 plus 9r power 2. So this is equal to root 169r power 2. Wait, okay, yeah, r power 2. This is correct, right? So what do? We have to simplify this further. So if you plug out this 169 root 169 r power 2, if you simplify this thing further, if you pick it out, this should be equal to 1 in parentheses 169 r squared, or in parentheses 1 over 2. The 1 over 2 will distribute inside the 169 r squared. And the r squared will cancel out 1 over 2. Hence we have r. Then for 169, 13 raised to the power 2 is the same thing as 169. Am I correct?
Yeah.
12 raised to the power 2 is 144. 13 raised to the power 2 is 169. Hence, the square will cancel the 1 over 2. Hence, you'll be left with what? 13r. Is that correct? Is that correct?
Yes.
Okay, let's show it here to make sure that everybody is carried along. So if you plug in everything here, this is equal to 169. So all this is equal to 13r. This is amazing, right? You can see how simple mathematics is. It just follows a very straightforward procedure. Once you're able to understand all these basic fundamentals without cramming and without cramming the rules, once you understand the why behind this, and not why and how, and not just the procedural method of understanding and comprehension. Once you're able to rationally and conceptually understand all these basics, you see that by the time we get to calculus, or by the time we get to advanced maths, you see that everything you are doing is you're just applying these basics, and everything will be going like. So let's solve the next example. So, okay. So, want to evaluate six power 4x minus 1 equals 1 over 216 all power 1 over 9. Solution. So from this, what do we do? So our aim is we want to find the value of x. We want to make x the subject. That's the aim. We want to make x the subject to find the value of x. So this means that whatever the value of x is, if we're able to find the value of x and substitute the value of x in that left-hand side of the equation and simplify, it will give you the same thing as everything you have here by simplification. 1 over 9, 1 over this. Whatever you have, you add the power and you do the power of this. It will give you like the balance equation. So the aim is what to make x is something. You want to find the value of x. We'll be applying both all that we have learned from expression, equation, indices mainly now. So from here,